So welcome back today to week 4 of the Open World Lifelong Learning course, the continual machine learning lecture. And today we're going to basically continue off where we stopped last week, which is we're going to continue talking about knowledge retention. So if you recall, in lecture 2, we talked about knowledge transfer and all of the things of how we can transfer knowledge to a new task. In machine learning, of course, this meant that we would talk about our parameters that we have learned useful for new tasks. And then last week, we've started discussing what about the opposite of it? Like instead of talking about knowledge transfer, what about the question of can we retain whatever we've already observed on our initial task, even though we continue learning new stuff? So we started talking about the 3 ways, or let's say 3 very popular ways of how to retain knowledge, how to avoid forgetting. And we've started going into details on 2 particular instantiations, namely regularization in terms of parameters and knowledge distillation. Now today we'll continue with rehearsal, and before I tell you what that means, let's just do a little bit of a recap as usual of the last lecture. So we recall that the undesired trivial solution, or perhaps almost trivial solution to continue learning would be that we could have a large amount of parameters and we could accumulate our data simultaneously. So of course we need to keep in mind, and we've discussed this last week, that if we are in fact constrained by capacity, then we won't be able to also learn indefinitely, meaning we won't be able to keep on accumulating knowledge in that sense. So on this graph that we had seen on the left of the slide, we'd observed that in a neural network with perhaps only 100 hidden units versus in a neural network with 1,000 units, we'd have a large discrepancy in terms of how long we could maintain accuracy in an online scenario where the examples on the x-axis keep getting permuted. And so for now, for this week's lecture, we will keep on staying in this scenario where we just assume that we have enough parameters, where we have a sufficiently large model so that when we learn a new task, we can actually capture this knowledge, and we'll ask ourselves the question, how can we retain whatever we've previously seen at the same time? So in the last lecture, we've had this illustration of the popular paradigms for continual learning, where continual learning here is in fact synonymous with the question of can we avoid catastrophic or gradual forgetting, mostly catastrophic forgetting. And we've seen these 4 illustrations here of what typically one could do. In A, we have this idea that we can train multiple tasks simultaneously, whereas then in B, C, and D, we have these ideas of how to go from a continual learning perspective where we don't want to have this naive idea of accumulating our data and having really large models. So instead, what we could do is we could train task 1 first. We could then identify all the important parameters, or respectively, like we've seen last time, we could check what the important input-output relations are, and we could then regularize or distill this information when we continue training on a second task data, on a third task data, and so on. Now today what we're going to talk about is this bottom right diagram, which is the D panel in this illustration here, which is all about rehearsal. So we're going to talk about this idea of having a subset of data where instead of accumulating a large data set and just storing everything, we pick a few particularly important instances that we keep on rehearsing to avoid forgetting. Now you'll notice that we're jumping from B to D here, although there's this C solution where we briefly also mentioned that there's this idea that we could maybe share parts and maybe extend the architecture, maybe also add experts on top. There's a reason why we'll discuss this after going into the rehearsal. It just fits the story better because the ideas connect in a more appropriate way. But most importantly, we'll also talk about active learning next week, and this entire idea of C also comes into play there quite heavily, which is where we'll now talk about rehearsal first. So long story short, let's get a little bit of an intuition for rehearsal. So first of all, I think it's important that we mention that rehearsal has an underlying assumption that storing data, first of all, is allowed in terms of privacy, meaning we're not violating some sorts of laws by retaining some of the older data. I think this is an important fact to mention because regularization, as we've seen last time, does not have this implication necessarily. And a lot of people might argue that continual learning is an effective strategy to avoid these privacy concerns to some degree, because we do not need to actually store whatever we've seen in the past. But setting this aside for a moment and assuming that it's okay to store some data, and also then assuming that we actually have some memory to store some additional data, we can talk about the idea which data we would like to store, coming back to the question of, is some data more relevant than others if we take a look at large data set? So on this example on the slide here, which we've seen in the past lectures, we've had this 2D binary classification task where we've previously argued that when going from the source training data on the left to the target training data on the right, we could identify the two hyperplanes as indicated in the picture that remain, that we could maintain in forms of knowledge transfer. And the other two hyperplanes, they would need to move if we're just interested in transferring to the target training data. So we'd said that in an easy or in a naive algorithm, we'd figure out that both of these hyperplanes need to be retained and the other ones need to be deleted and moved. Now, today the question is then, how could we maybe also maintain the old hyperplanes, so not move them, but keep them, but also then transfer the two hyperplanes at least that we have that are beneficial to the target data at the same time. And the question is, how can we do this by potentially storing as little data as possible? And if you look at this example, it maybe becomes clear that one idea would be that the main data points that are responsible for these two hyperplanes here are the ones that are immediately on the left or on the right to it. So if we look at the zeros that lie on the complete left, then the zero that's closest to the hyperplane is perhaps more important for the hyperplane than the one that's far out, because the far out one doesn't necessarily provide any additional information. So if we think of maybe one potential subset of data that we could store that would avoid forgetting to a large degree, it could be these three data points illustrated with the red circles here. So we store one of the zeros on the left, one of the ones in the center, and one of the zeros on the right. Now, maybe this isn't the perfect solution because the hyperplane we can then draw can still wiggle a little bit to some degree, so we'll make some minor mistakes. But roughly speaking, the catastrophic forgetting in that sense would be prevented. And so this is the intuition behind Rehearsal, where the question is then, which data do we store if we want to even store as little data as possible? And instead of going through all the desiderata and all the things that we would like to have and all the assumptions that we could maybe make, as we've done in the previous lecture, in this lecture today, I wanted to start with a practical example. So what we're going to do is we're going to discuss one very prominent work in the literature, which is based on this idea of nearest mean classifiers that we had also seen in lecture 2. So recall in lecture 2, we briefly talked about these ideas on few-shot learning and zero-shot learning, one-shot learning. And we had said that one idea to potentially approach this is that for each concept that we have in a supervised setting, we could get a prototype such as the mean vector of each class that we've observed. And then instead of building a classifier purely based on some prediction function, we could also do this more explicitly by taking into account then the distance, so some distance function, be it Euclidean distance, cosine distance, which measures how far or how close we are to the prototypes that we've selected in a embedding space. So typically the embedding space would be a neural network, for example. And now note here that the nomenclature is not consistent. So some of the literature like few-shot learning calls this prototypes. We are going to call this exemplars in a second in the works that we're going to see for continual learning. The more formal approach would be called core sets, which we'll get to at the end of the lecture. But just as a small summary, the idea here is that these prototypes, so the mean vectors of each class, maybe these could be important data points to store, or at least give us the area around which important points to store lie. And this is the essence of one of the most popular rehearsal-based continual learning strategies, which is called ICARL, which is short for incremental classifier and representation learning. So the three main points of ICARL really are that, first of all, it assumes that the setting is allowed where we do store a subset of the data. It does so in a fixed-sized memory buffer, meaning there's a predetermined amount of data points that we want to store, and this never sort of changes. There's a classifier, which is based on this idea of nearest class means, so meaning we classify by checking where we are closest with respect to these so-called prototypes. And then when we learn continually, there's a third component which consecutively replaces parts of the memory buffer with new examples, because given that our memory buffer has a fixed size, we're going to populate this completely at all times, and when new concepts come in, we'll figure out which parts we maybe remove to accommodate the new concepts in addition, so make some place for new concepts. The classifier algorithm is shown on the right on this slide. You can see that it's fairly simple. It's really nothing more than what we've just said. It's this idea of having these means of, in this case, then exemplars in the memory buffer, but overall just the means of classes. And according to these means, we'll get a prediction for a target label given a simple distance function. And so we'll predict the class that's where we find the nearest prototype, the nearest mean of exemplars. Now then, the important question, or the main question that we'll look into today, is not this idea of the nearest mean classifier, but more importantly, how can we do this rehearsal and how can we avoid catastrophic forgetting, which really boils down to the question of how do we fill this memory buffer that we've allocated with specific examples that are meaningful. The particular technique that ICARL proposes or makes use of for their scenario is an idea called herding. And so herding in this framework of a nearest mean classifier, what it's going to do is it's going to pick exemplars to best approximate the overall mean at all times, and it's going to do so iteratively. So what we'll do, as we see on the right-hand side in this construct example set algorithm, is that assuming that we have some current feature function, so like a deep neural network that maps the input to some feature space, we're going to start calculating the current class mean of all the data that we've seen, so the real data, and then according to these class means that we're going to have, we're going to start populating the memory one by one, so looping through the entire sets of k amount of memory exemplars, and each time we're going to add one instance to the memory buffer that is going to lead to the overall best approximation of this entire current class mean. So if you think of this geometrically, if you have a mean at the center here, maybe in the first time you'll pick one that's here, and then the second time you'll pick one that's exactly in the opposite, so that the overall mean is always best approximated by the data that you pick. So on the one hand, the more we pick, the closer we're going to get to this mean. But on the other hand, it's also very computationally expensive to actually do this, because we're going to loop through each and every single data element k times. So it's a quite computationally expensive procedure. The advantage, however, is that if we do it, or at least the advantage that's argued by the paper is, however, that if we do it this way, by going iteratively one by one, we know that as soon as we have some exemplars in the beginning, we're going to have a mean approximation that's decently nice already. So say that we have 20 exemplars in the memory buffer, we know that our mean approximation is maybe decently close to the real mean. So what the argument is that as we continue populating this memory buffer, we're going to realize that the examples that we add later contribute less to this mean estimate than the ones that we had in the beginning. So in that sense, the question of when we have populated this memory buffer on the first task and then need to populate additional instances from the second task by making some space, this idea of reduction or how to reduce the memory buffer is really simple, because we already have something like a prioritized list. So in that sense, we could take, for example, 100 examples on the first task of ICARL, and once we see the second task and we want to maybe go 50-50, we'll just chop off half of the list in this initial memory buffer, because it got filled through this loop of k times one by one. And so in that sense, the question of how to reduce the example set is really trivial, as we can see in this right hand side algorithm, where it's nothing else than keeping only the first so many elements. And so the last question we then need to ask ourselves is, we now have this idea of how to populate the memory buffer with this nearest mean idea and this herding algorithm that just goes iteratively one by one. And we already have a quite easy and intuitive solution of how to chop the memory buffer to again repopulate it as soon as the next tasks come in, because we don't only want to avoid forgetting on the first task, but we also want to avoid forgetting for each task in sequence. So the only remaining question is, how do we train this incrementally now? And it turns out that let's say the initial solution of the original ICARL paper, which is now already 5 years old, is relatively simple in this regard. And as you can see on this left-hand side algorithm on updating representations, the idea is really just to form a combination of the current task training set and the stored exemplars that we have. So it's really just take this memory buffer and concatenate it together with the real new task data, and then just keep on optimizing and do your thing with updating the representation with whatever algorithm you use, typically, as discussed before, gradient descent. The reason why we're also picking ICARL today is, as you can see on the bottom half of this algorithm, it also has a dual form loss function, where in fact ICARL does not only do this rehearsal, but it also incorporates the concept that we have visited at the end of the previous lecture, namely knowledge distillation. So in addition to maintaining this subset of memory of data instances in this memory buffer, we're also going to apply a distillation loss on top. We can discuss in a second, or we will discuss in a second, whether that's important and why it's important. But for now, let's just acknowledge that ICARL has an additional knowledge distillation loss, and it's doing this exemplar rehearsal at the same time. Let's take a look at this quantitatively of what has been reported in the paper and figure out whether we are maybe surprised by this, or whether we are whether we're seeing exactly what we expect in these plots. So the plots show a dataset called CFA100, which is 100 different tiny objects and images. So it's 100 classes ranging from cars to some animals and some other objects. And here in this very left plot, we can see an incremental learning procedure where the tasks are introduced with 2 classes at a time. In the center panel, we can see the same sort of experiment, but in each task increment, there are, I believe, 5 classes introduced at a time. And on the very right-hand side, we can see that each task corresponds to the introduction of 10 classes over time. Now, there are 4 methods that are being compared in this diagram. The first one is the one where we would expect catastrophic forgetting to happen. It's this very light blue one, this turquoise one, which is called fine-tuning here, which really just corresponds to this idea that we've discussed, where you just start training on one task, and then you just remove the data and continue training on the next task, and so on. And well, since we've said that our optimizers are greedy, what will happen is we'll just overwrite our representations, and this is quite visible in this curve here, because the accuracy at any time is really just the pure accuracy on the current task, and everything else is random. So if we have only 4 classes, we'll get a 50% accuracy, because 2 of them will have almost completely accurate, and 2 of them will just have random guessing. We can then compare this to the fixed representation curve, which is the red one, where this is what we've discussed in transfer learning, where the idea would be that, okay, but maybe we've trained on the initial 2 classes, the initial 5 classes, the initial 10 classes, and maybe those representations are already good enough so that we can freeze them and we can get some sort of transfer. And indeed, what we can observe here is that on the very left-hand side, where we only start training on 2 classes, this doesn't work at all, because 2 representations for 2 classes are not particularly reflective of the remaining 98 ones. But of course, when we go to 10 classes in the beginning, we can see that this helps a little, but nevertheless, we'll still get a lot of forgetting. And so the main 2 important algorithms that are being compared to here is this learning without forgetting algorithm, so this knowledge distillation idea that we've ended the last lecture with, and the ICARL idea, which in addition to the knowledge distillation loss, now also adds this key component of rehearsing these exemplars that were filled with this herding algorithm. Now, in all three of the panels, we can see that ICARL majorly outperforms the learning without forgetting one. In fact, we could see that maybe ICARL does decently well in all of these scenarios. Of course, what is missing from these plots is there should have been some sort of upper bound in the sense of how much, given a specific architecture and specific learning parameters, would you have actually expected to achieve, given that you had accumulated all data. Now, from experience, I can tell you that in CIFAR 100, with the architectures that have been used in this paper, you would have likely gained something like 65%. So in that sense, ICARL is still suffering from a little bit of catastrophic forgetting, but maybe not as much as the other just knowledge distillation-based approach did. We can confirm this intuitively, visually, when we look at the confusion matrices that have been shown in the paper, where on the very left-hand side, we can see the predicted classes for ICARL. So quite nicely, we can see that the diagonal, so the actually true predictions that we would like to have are highlighted quite prominently. In the learning without forgetting, we can see that this is also the case for the bottom right, so for the tasks that we have seen very recently. But the more we go into the distant past, we can see that there is actually forgetting, somehow implying that this continuous distillation over and over again is has its limits in terms of how many times we can repeat this, in contrast to having this additional component of storing some of the original data. In the right two panels, maybe those are the most intuitive. We can see what would happen with fixed representations. So not surprisingly, in this example where we started with 10 classes, we could see that the first 10 classes are always kind of predicted because the neural network here is heavily focused on the representations for the first 10 classes. So we are unable to learn any of the newer concepts really. And in the fine-tuning case, where we just continue tuning on whatever we currently see, we also are not necessarily surprised because all that we're predicting is whatever we've seen last. So only the last 10 classes we've seen. So we've seen that ICARL shows some initial promise if we look at these quantitative results, and we could now believe that it's a okay solution to combat catastrophic forgetting by combining this knowledge distillation with this idea of having this herding algorithm to fill a memory buffer. But of course, the scientific questions behind it would now not only be whether we can store a memory, whether we can populate a memory buffer, but the scientific questions would be whether the algorithm with which we populate this memory buffer is a good one, alongside with some other questions that we'll see on the next slide. So in this diagram here, a follow-up paper has actually revisited distillation and incremental classifier learning in the form of ICARL and has asked itself the question, what would happen if we do this exact same experiment multiple times here? So you see the standard deviation bars. Once where we populate the memory buffer with the herding procedure. So just to repeat this idea of having these nearest means and going one by one to always add the example that best approximates the overall mean at all times, versus what would happen if we actually pick the data instances with which we populate the memory completely randomly. So just uniformly at random pick k elements from the data set. And as you can see here in this plot, it does not really make a difference. So somehow what this is suggesting is that although the entire idea of elaborately populating according to nearest means and prototypes and having this as a basis to have this exemplar selection, it sounds very elaborate, but maybe it doesn't yield the quantitative benefit that we would have expected it to have. And that is, of course, not the only question, but the second one is, how expected are actually our observations? So now that we figured out that randomly picking data instances and populating a memory seems to be as good as this herding procedure, the other question is, how much of an impact does the size of the memory buffer have? And again, not surprisingly here, what we have is a nearest mean classifier, an ICARL, and we can see that when we look at the x-axis, the memory buffer size grows, and linearly, or almost linearly, I would say, in terms of relationships, so does the accuracy. So the larger the size of the memory buffer, the larger our classification accuracy in this scenario will get, which again, if we think about it very carefully, is not surprising at all. So it's a little bit maybe almost frustrating if we think about reading papers that do rehearsal and continual learning, where, for example, there isn't a very clear analysis of how the memory buffer size affects the results, because quite intuitively, we've said that the trivial solution is to just maintain the entire data set, assuming that we have enough capacity. And so naturally, the closer we get to this entire data set, the better our results are going to be. So really just looking at the absolute result in terms of accuracy is not very meaningful to do unless we frame this from a perspective of a fixed amount of examples that we've chosen and then compare which of the algorithms by which we populate the memory buffers perform worse or perform better. Taking this to a little bit more to the extreme, another follow-up paper, and it's here for me a little bit surprising that this has been done only 2 years ago. So it's a very nice work where the question was how much of this entire ICARL or how much of this entire rehearsal idea is really just the key concept that we just store data in the first place. So going aside from all this, like what is the correct algorithm with which we pick exemplars, and maybe even how do we interleave it? So ICARL has concatenated the data sets. We could also think of, rather than concatenating the memory buffer with the data set, we could maybe always sample a little bit from the memory buffer and always sample a little bit from the data set in each step in terms of stochastic gradient descent, so that each mini batch is composed a little bit from the memory buffer, a little bit from the current task. But taking all of this aside, what this paper has done, and it's calling it a greedy dumb learner, is that they just greedily sample, so again, just randomly sample to populate a memory buffer as they see the data, and then they pick this memory buffer aside and train another neural network, in this case, from scratch. So it's a dumb learner, and it's a greedy selection mechanism. So it's greedily populating the memory buffer, and then it's just a really dumb learner, which doesn't make use of any past knowledge. It just trains on this memory buffer by itself. And so I'm not going to show you all the quantitative results of this paper, but essentially the summary of this paper is that for the tasks considered in ICARL and some related papers, this dumb, greedy approach of training alone on the memory buffer almost always yields the same or a very similar accuracy, sometimes even outperforming what has been reported in this scenario where you first learn on one task, then on another, and so on. So in that sense, it's letting us question a little bit the role of memory and the role of exemplar rehearsal, because it's a fine line between this, how trivial is what we're getting, how good are the algorithms with which we selected, but also the question of, are we really doing better in terms of continual learning rather than just learning from scratch again, given that we've already maintained or retained a data subset? So as an alternative to this idea of just storing and rehearsing data subsets, there have been arguments for a long time now that memory buffers of real examples maybe are not the only or the, let's say, alone solution to continual learning, even though if you look at present literature, they are maybe by far the most popular approaches because of their practical accuracies that are maintained. So reading this quote from a pseudo-recurrent connectionist networks paper on the sensitivity plasticity dilemma that we've talked about, it says here, while it is an effective method in artificial neural networks, rehearsal is unlikely to be a realistic model of biological learning mechanisms, as in this context, the actual old information is not available. Pseudo-rehearsal is significantly more likely to be a mechanism which could actually be employed by organisms, as it does not require access to this old information, it just requires a way of approximating it. So what this quote is saying is that the idea maybe to rehearse is not the culprit here, but the idea that raw data is rehearsed maybe isn't the smartest thing to do. And it's mentioning pseudo rehearsal here as a buzzword, as an alternative, which we're going to take a look at now. So it's another strategy for rehearsal, but rather than picking raw data in its initial form here, we can see that pseudo rehearsal is based on the use in the rehearsal process of artificially constructed population of pseudo items instead of the actual previously learned items. And so in this quote here, a pseudo item is defined as constructed by generating a new input vector, setting at random 50% of input elements to 0 and 50% to 1 as usual. Now, keep in mind, this has been a binary task, a binary classification task, so it's maybe an obvious strategy of how to populate it. But what it's essentially saying is that pseudo generates some input data. So don't retain the original data, but pseudo generates some input data. Maybe some noise, like in this case, feed it through the network, through the machine learning model, and then whatever output vector this input generates becomes the associated target output. So you can, again, do this entire distillation idea and keep on optimizing, but not on the original raw data. And so if you look at the inspiration from this quote and maybe the inspiration for not only pseudo rehearsal, but in a broader sense, maybe even the data rehearsal idea, it comes from a neuroscientific perspective of complementary learning systems theory. So I'm not as I've said before, I'm not a neuroscience expert, so I'm keeping this pretty simplified here to the degree of my understanding. But if we look at also recent reviews, the popular example is that there are two models or two systems that interplay with each other hypothesized in the brain, although I think hypothesized here goes beyond it. I'm pretty sure it's been experimentally confirmed to large degrees, where there's the hippocampus, whose role is to have short-term adaptation and rapid learning of novel information. And there's the neocortex, which is more about slow learning and consolidating and building up the overlapping representations. So in these two systems, one is really all about how can we rapidly get information from new stuff, and the other one is then questioning how can we integrate this into what we already have. And the idea here is that there's an interplay between these two systems because the hippocampus, which acquires this rapid novel information much more faster, can then somehow play back to the neocortex to consolidate the memory, to consolidate the knowledge. And so if you think of the most intuitive thing here, or where this hypothesis comes from, is this idea of REM sleep, where once you start sleeping, there are these REM phases where you see like a lot of activity in your brain, where it's assumed that patterns are being replayed so they can be consolidated into your memory so that the ideas that you've observed during the day can be manifested more properly. And so naturally, we can take this idea and think of whether we can now use this in our machine learning systems. So rather than just having a single machine learning model, we could ask ourselves, can we just train two machine learning models, where one is something like a generator, and the other one is something like the actual task solver, and then we just alternate the training. And so the generator here is called the generator because what it's going to learn is it's going to learn how to generate the data. So going to learn how to replay data-like inputs. And the task solver can just be whatever we've already previously considered. So it could be some neural network or something that solves the task. Now, note that the generators are quite varied in terms of the types they come in. So currently, I think the popular ones are normalizing flows, there are variational autoencoders, there are diffusion models, Gaussian mixture models. So there are a lot of different generative approaches, which we'll go to in a second. But the key idea is really here, again, on the slide illustrated maybe in a more intuitive fashion, that rather than rehearsing the subsets of the original data, we'd have some training data. And with this training data, we learn a generator at stage 0 to generate patterns that look like this training data. So in this case, zeros. And then we go ahead and feed in maybe the ones here and just see the ones in our solver as well. And the generator keeps on feeding the solver with data generated from old tasks so that it doesn't forget. So it's maybe, let's say, inspired by this complementary learning systems theory perspective, but then very loosely interpreted in the way it's conducted. So in the most naive form, what you could really do is you could just train a solver on zeros, train a generator on zeros, let the generator create a data set of zeros, concatenate this with a new task of ones, train the solver on it, and so on. So you don't even need to do it in like a simultaneous fashion, but you could really do it in this way of slow versus fast learning, where you just train these systems separately, and then the generator keeps on replaying to the solver while the solver keeps on learning. So looking at the specific paper, which has maybe done this for the first time in deep learning, called Continual Learning with Deep Generative Replay, they have used the generative adversarial neural network, if that is something that you know about. If not, it doesn't really matter. Just assume it's a neural network that has learned how to produce the data it has observed. And it's been compared here with exemplar rehearsal and this idea of pseudo rehearsal based on noise on, I believe it's an MNIST task here. So the digits that we've seen on the last slide progressively introduced in pairs of 2. So what we see on this diagram on the right is the accuracy versus the number of iterations with these 5 task increments. First of all, we can observe that this idea to just pseudo-rehearse random patterns in terms of noise does not actually work much better than not having any rehearsal at all. If we think about this for an instant, maybe it's not so surprising, because the noise patterns that we generate would no longer reflect the real data in any meaningful way as soon as we go to these handwritten digits in some form of images, because they have a spatial structure, they have a specific type of handwriting and strokes and so on. So randomly rehearsing noise patterns is maybe not surprisingly much worse than not having any rehearsal. But what we could also see on this slide is that the experience replay, so this idea of rehearsing the exemplars, this memory buffer with explicit data, is on par with the generative rehearsal version, where we have this powerful generator. And of course, the question that we have here, or that we need to solve, is having a generator that's actually powerful enough to generate something that's meaningful with respect to not only maybe looking alike, but also being distributed similarly to the original data. And so what we'll do now, before we cycle back to continue learning, is we're going to take a short interlude on generative models, primarily summarizing the idea behind generative models, and then taking a look at a specific example here of a generative model, so that in addition to ICARL, we can take a look at a second very concrete approach to continue learning based on generative rehearsal and not just based on rehearsing original data. Now, it may be that you're already familiar with this, so in that sense, if you're watching the video, you can skip ahead. Although I do believe that the interlude that we're going to have here on generative models is going to be quite nice, because the example that we're going to take a look at are autoencoders and variational autoencoders, so that we can take a look at variational continual learning. So taking a look at the math and the system again will help nevertheless. So I encourage you to just stick through it and keep on watching, rather than thinking that it's something that you know about. Now, just as a short reminder with respect to what we mean when we talk about a generative model. So a discriminative model, we typically learn something like a prediction function, such as predict the labels given some input. And in contrast, in a generative model, what we'd also learn about is the data distribution. So we're interested in really the process by which data is created. So the generative factors by which data are created, where the name is now coming from. Now, what we should keep in mind here is that generative is not necessarily just synonymous with the fact that we can, for example, create a pretty image. So not every model that maybe creates a pretty image of a handwritten digit, for example, is necessarily a generative model, because it does not necessarily learn about the data distribution formally. But also we can keep in mind that although generative models are often unsupervised, they are not by definition unsupervised necessarily. So generative models can in fact also learn discriminative tasks. because what we could always do is, instead of just learning about the data distribution P of X, we could learn about the joint distribution of P of X and Y, our labels, and then we could do a factorization as shown on the slide, where we still get this prediction of P of Y given X, but supported by the data distribution, supported by P of X. So as I've just said, the concrete example we're going to look at is a variational autoencoder as one type of generative model, as one type of neural generative model. And in order to understand what a variational autoencoder is, let us just super briefly introduce what an autoencoder is. So an autoencoder is shown on this left image here on the slide. And what it's really just doing is it's, first of all, learning a representation of the data into some usually compressed space, which we refer to as the latent space or the encoding, which is illustrated in the red points here. It's going to do so through many different means, but typically through a neural network as the encoder, so some sort of fully connected neural network here. It could be convolutional, it could be recurrent, etc. But the idea is just that you have some sort of transformations that go from the original data to some typically compressed latent space that encodes the data. And then from this encoded data, you go again through a decoder, which maps this compressed space back to a reconstruction of the data. So the objective that we're going to formulate here is going to be something like what we've seen on the second in the second lecture on optimization, where we talked about for example, the mean squared error loss. So the mean squared error loss could be something that you could apply here. So you don't necessarily need labels for this. You could just, as an optimization criterion, as a loss function, you could take the absolute deviation or the squared deviation between the output that you reconstruct and the original input. Now, the main difference, which we're going to see now between an autoencoder and a variational autoencoder, is that the form of this embedding, the form of this code that we learn in an autoencoder is not really explicitly constrained. So meaning it's going to produce some sort of embedding, which can, of course, be very useful, but we don't really know what type of shape it takes on, what type of distribution it follows. So the main gist of a variational autoencoder is to add an additional constraint to this latent space so that it follows a specific distribution. So here you could see in this example an image of a cat being reconstructed, and these red dots of the encoding of this latent space, they're being replaced here by a mean vector and a standard deviation vector of some distribution. Here it's going to be a Gaussian, but of some distribution really, from which we could sample the latent vector from which we know the latent samples originate. And to understand this more formally, because it's advantageous to then talk about continual learning with these type of models and then generative rehearsal prospectively, I would like to just more formally walk through this once. So what you're going to see on the next slides is a derivation of a variational autoencoder in a more formal mathematical way. We're going to do this rather than going from the entire model and sort of tracking back what we've done in order to understand where this all comes from. We're actually going completely inverse. We're going to start from scratch and derive the variational autoencoder from there. So I hope you're going to appreciate it, but I understand that there are other ways to derive variational autoencoders which you might prefer. Anyhow, let's formally consider, just notation-wise, a data set with the variable x. We'll now consider that this random process by which the data is generated involves some unobserved random variable which we call z. And this z is generated from some prior distribution. So some distribution where we have a belief that this is a good distribution, and a value x is then generated from some conditional distribution based on these random unobserved variables set. The first problem, or let's say the mathematical problem that we have in this formulation, or the general mathematical problem in variational autoencoders, is that we can, of course, say that there are some random variables z, some latent variables z, and that there's a random process by which data is generated, but of course we don't know this. And so what we typically mathematically have to do here is we'd have to integrate over all the possible values of z, so really have this integral over p of x comma z dz, and find out what this tells us then about px by integrating over all these variable choices. But naturally this is intractable, or I don't know if it's natural, but it's intractable. And so what this means is that there exists no efficient algorithm with which we could solve this. So what we're going to do in a variational autoencoder is we're going to derive it by having a bunch of tricks by which we could still arrive not necessarily at a solution, but at a lower bound solution, which we'll understand in a second of what that means, but some sort of quantity that tells us something about the p of x which we desire about the data distribution. And we're going to do that at a hand of a couple of, let's say, sub-tricks, and in addition, using Bayesian inference, so using the idea that we can switch probabilities here through Bayes rule, and we can relate probabilities here through Bayes rule. Now, Bayes rule is at the top of this slide. You can see that basically what Bayes rule is going to tell you that on the left-hand side, you have this notion of a posterior. So in a sense, it's the degree of belief that after incorporating some evidence, like from the data, some of the data, you have in your latent variable set. So it's this p of z given x. And you could reform this through Bayes rule on the right-hand side into, first of all, a prior distribution, which is this p of z on the top right, which we refer to as our initial belief. And the remaining part is this quotient of the marginal probability distribution on the bottom p of x and this likelihood term p of x given z, which really what this quotient tells us, it's the support that x gives us for our z. And so using Bayes rule, we can then start reforming these terms with the essential goal of getting rid of all these terms that we don't know about and maybe keeping the terms that we can reason about practically. What we'll first do is we'll get it into a more convenient form by making use of logarithms on both sides to write out whatever we have on the top as a sum. So you may recall that logarithms are quite nice here because a product of logarithms can be reformulated as an addition, whereas a quotient is boils down to subtraction. So really what we're just doing is by introducing logarithms everywhere, we can reformulate this rather not so nice looking parts on the top into a one-liner where we just have addition and subtraction in there. The next thing that we'll realize, however, is that, and I've just said this, there's still some parts in here which we have absolutely no clue about. More specifically, we still have this idea in here of the log of p of z given x on the very right, which is also where we started from on the last slide, where we said that this is something that we don't know. This is something that we would have to like integrate out variables and so on. So it's quite complicated. So we don't really know this real posterior. And this is where the variational in the variational autoencoder comes from, because what we're going to do now is we're going to introduce an approximation to this distribution. Rather than calling this approximation then p of z given x, we'll just call it q of z given x. And then the first step all that we're going to do is we're going to plug in this approximation by introducing an integral over this approximation q of z given x dz. So it looks like we've done something very magical here. But again, if you think about it for a second, and if you're familiar with probabilities, we've not actually introduced anything rather than a 1, because integrating over q of z given x over all dz's, it's a valid probability distribution. It's going to give you 1. So in that sense, we've not really introduced anything. But what we can now do is, and this is maybe the least intuitive step, because unless you already know the solution, it's maybe not so clear why we're going to do this, is what we can do is we can also add and subtract another two of these approximations. So we just add a plus q of z given x and a minus q of z given x. So we don't add anything, it's just a zero. But the reason we do this is because there's a quite nice mathematical definition, a quite nice way to reason and measure about measure and reason about two distributions. So there's this concept of callback labler divergence, or the reverse, depending on how you flip the two probabilities, which is going to measure how distant two probability distributions are, or how similar they are. And the way this definition works, as you can see it on the slide, is that if we have two distributions Q and P, we're going to take a look at the integral over one of the distributions times the log of the quotient of the two distributions. And so now if we look at the top equation here, and we might have to do this like very slowly because we'll need to like look at all the individual components one by one, we can see that due to this, first of all, multiplication that we've introduced over the integral with sum to 1, we have the q of z given x multiplied to each and every single term in the brackets. And then, due to the way we've added and subtracted the q of z given x, where we've just added 0, we have made sure that we can now make use of this log of q divided by p, because recall, log of something minus log of something is also just the log of both of these terms in division. So we can take this definition, which measures the discrepancy between two distributions, in this case our real distributions p and our approximation to it q, and we can reformulate our top equation. So first what we're going to do is we're going to take the term where we multiply q of z given x by q of z given x minus the p of z given x, and we're going to make one KL divergence out of it, which is this first term. And we're going to have another KL divergence, which is going to have the q of z given x and another of the added q of z given x's with respect to our prior distribution p of z. And what is then remaining is still this log of p of x given z, so this likelihood term, which we're going to say that rather than evaluating this nasty integral, we'll evaluate it through some sort of sampling process where we just draw samples of z from this distribution, and then we can calculate this term approximately. We're going to say how we can do this expectation part in a second. But most importantly for now, we've re-expressed our start by doing these mathematical tricks, where instead of having all these different terms now, like posterior and the likelihood and prior, we have these KL divergences between our approximation and the real distributions. Most importantly, however, we still, just as on the last slide and the one before and the one before, we still have this term of p of z given x in there, so this real posterior that we started with and still don't know about. But now comes the important trick, which is the key to the variational autoencoder, because what we can say is that a KL divergence is strictly positive. It is a measure of information of how we can distort one distribution into another, which is always a positive amount of information. It can never be negative. So what we could say is that let's not care about this term necessarily. Let's express our loss in the with the other terms and keep this KL divergence term as is, because what we can say is that given that we know that it's strictly positive, we can put it on the other side of the equation, and instead of saying that we now learn about the log of p of x, we can say that we learn a lower bound to the log of p of x by subtracting the strictly positive KL divergence. So meaning we're not really going to get the accurate exact solution to a problem of learning about p of x, but we're going to potentially get reasonably close or sufficiently close to this solution so that it satisfies our needs. So what we'll have is we'll kick this KL divergence term between the approximate posterior q of z given x and this real posterior p of z given x. We're going to kick it out and say that instead of having an equal sign in this equation, we'll have a lower than. And so the remaining parts that we're going to have are these two here, and we'll find out now that both of these terms we can luckily evaluate. So the first term is this log of p of x given z. So what this is, it's actually the likelihood that x comes out of these latent factors of these generative variables z. And this is basically, if we think back of our autoencoder, it's something like this reconstruction error, this reconstruction loss that we have, with the addition that this expectation involves some sort of sampling step that we'll see on the next slides. The second term now, it's that's the additional part in the variational autoencoder, in contrast to our autoencoder. It's this KL divergence. Now this KL divergence here, what it's actually measuring is it's measuring this approximation that we've introduced, so this approximation to the real posterior, and with respect to the prior. Now keep in mind the prior was something that we said is a belief from our side. So it's something where we'll make a choice in a second of what we believe the latent variables, the generative factors, are distributed. So if we put this into the variation in the autoencoder perspective here, what we can say is that this encoder part here could give us something like this approximation to the posterior, and it's going to produce some z. And this z, we're going to say we measure the KL divergence of how much whatever we get from this encoder corresponds to the prior belief that we've had, and then we reconstruct it. Now, if you want to learn more about like the very sort of nuances of KL divergence and what KL divergence exactly measures, I'm just going to summarize it here, but there's a really nice blog post on the bottom that I encourage you to read because there are a couple of subtleties around it. Mainly what KL divergence is going to do is it's going to measure the amount of information in natural units, not nets, but nuts, in natural units or units of 1 over log 2 bits that is required to distort one distribution into another. And of course, if you, for example, minimize this KL divergence, what you're going to get is two sort of distributions that lie close to another. Now, there's a rather bigger twist with respect to this formulation, and you can see it in this blog post, it is that KL divergence is not symmetric. So it makes a big difference whether you think about how to distort P into Q versus how to distort Q into P. You can see it in this blog post, but it boils down to the question of, for example, if you have a distribution with 2 modes, are you going to approximate one of these modes very exactly and omit the other one, or are you going to sort of envelope over both of them? We'd actually like to do sort of this envelope idea where we're going to say that we'll find some parameters that are now responsible to find this variational approximation, to find this Q of Z, and we're going to say this is a probabilistic encoder, and it's this approximation to this intractable posterior P of Z given X that we had. So just as an intuitive sort of expression, it really means that given a data point X, it produces a distribution over possible values of Z from which it could have been generated. And then this from which it could have been generated idea gets into the probabilistic decoder, which is like the second half that calculates the other way around of the probability of P of X given Z, which really means that it produces a distribution over all possible values of X given Z. I'll show you an example in the next slides now after we've gone through the rigorous math. You'll find out, I hope you followed at least a little bit through the rigorous math. If not, it's completely understandable that this is a rather challenging concept. But there are some really nice variational autoencoder tutorials on archive that were referenced on the former slides. They are quite lengthy, but it may be worth it to go through them if you're interested in this. If not, I'll just explain an example now to give you the intuition of why we should care about this, and then continue why we even did this entire excursion in the first place with respect to continual learning. So the example I'm going to pick is we're going to take an approximate posterior as a multivariate Gaussian, and we're also going to assume that the prior belief that we have, this prior P of Z, is also a Gaussian in a second. Now on the right-hand side, you can see that a Gaussian, it has 2 central variables, right? It has a mean and a standard deviation. So in that sense, what our probabilistic encoder would put out is a mean and a sigma vector if you want to make this multivariate. And so then this gets, you sample from it, you get a Z, and you feed it into the decoder and you reconstruct. The only issue now is that this distribution itself and the mu and the sigma and the samples, they're all part kind of this optimization part in a model. And it turns out that this is rather difficult to optimize in practice because of issues around having to draw a lot of samples, and then there's high variance in the updates. So it's something that's not very convenient to do. And so what we'll do in practical variational autoencoders typically, and this is usually what you'll find on the internet, in papers, in practical applications on GitHub, is you'll make use of a reparameterization trick. So the reparameterization trick is going to tell you that rather than generating samples from this Q of Z given X, this approximate distribution that we have explicitly, as with random variables, you'll treat it with Z as a deterministic variable. And you can do this because quite nicely for Gaussians and also a lot of other distributions, you can reparameterize by sampling something, multiplying it to the standard deviation and adding the mean because of this additive property. So what we can say is, for example, that we can pick a prior P of Z as one choice, which is a unit Gaussian with mean 0 and standard variance. And we can take a sample epsilon from this distribution instead, so 0, 1, and then whatever comes out will multiply by the sigma of the encoder and add the mu vector of the encoder, and we'll have a valid sample of Z. So rather than sampling directly from this encoder output, we'll sample from the 0, 1 distribution and we'll reparameterize to this addition multiplication and to a valid sample of Z. Now, why are we doing this? What's the advantage? The advantage is that this distribution, this prior P of Z, it's not actually explicitly in our optimization path. It's on the right-hand side here. We don't need to optimize it. It's just something where we sample from all the time. And we can just use conventional stochastic gradient descent backpropagation to just update the parameters of decoder and encoder, where we just treat this mu and the sigma as kind of a static, as a deterministic output. And so it's a quite nice trick, which is about optimization that we can do here. And so intuitively, what this really means is the following. If we take this variational autoencoder and now draw it with this reparameterization trick, we're going to have this green part in this diagram here, which is our probabilistic encoder, which tries to learn about this Q of Z given X. But we're not really going to have this sampling like directly, but we're going to have this reparameterization trick where we sample from this unit Gaussian, as you can see on the bottom here, and do the reparameterization. And this is actually our prior belief. This is our prior P of Z. And so what the KL divergence that we have in this equation that we've seen mathematically before really tells us then is try to press whatever really comes out of this encoder into this P of Z, into this unit Gaussian that we want it to be, that we assume is our belief. And we can do that because the encoder will typically have so many parameters that this will be possible without really having too big of a trade-off. And then you can have the decoder reconstructed. So we'll calculate the reconstruction, the likelihood that the X generated from the specific set. Okay, so maybe a long detour. I hope I kept it decently short so that it's not too boring in terms of we're only going to talk about variational autoencoders today. But I'm also hoping that for the follow-up slides, I have kept it sufficiently detailed, maybe if you go through it again slowly but, through the recording, that we can understand why this detour was important and we can come back to continual learning. So what I'd like to do now is try to relate this to the continual learning idea, specifically also the rehearsal idea, but also the concepts we've talked about last week, to understand why, in my opinion at least, this is a really cool approach to continual learning. Now, first of all, what have we gained by going from this autoencoder or just any neural network perspective to this variational inference perspective? Now, keep in mind that we've already talked about embeddings in few-shot learning, and we've talked about we can calculate distances here, but we've never really had, or we usually don't really have a very explicit form of what this embedding looks like. Now here's an example on the slide where we can take a look what happens when we add this KL divergence term rather than just having an autoencoder with a reconstruction loss. So on the very left, you can see a two-dimensional embedding. So the latent variables are really two-dimensional on a 10 class task. It's trained in an unsupervised fashion, so the class labels are not provided, but you can see what the embedding looks like, given that you've trained optimized for reconstruction loss. And so the first thing you'll observe is that there is some sort of class clustering. So the ones, for example, that they are kind of close to another because they resemble each other. And you can also see that you can maybe have some sort of arrow where you go from 1 to 7, but on this arrow, you can see that there are parts of the embedding space that are essentially empty. So where no viewed data essentially lies. So it's questionable what this part of the embedding actually means. But of course, through distances and prototypes, you could still argue, is this closer to 1? Is this closer to a 7? It works because if you think of reconstruction loss and if you think of compression, the reason these similar instances are close to another is because it's the easiest way to then reconstruct, because it's the most efficient way to compress, to keep concepts that are related close to another. Otherwise, you would have to create a lookup table, and a lookup table requires a lot of capacity. So if your autoencoder has a latent space that is smaller in terms of dimension than the original data, it'll typically try to put concepts that relate to another close to each other. So that's why this entire idea of embeddings kind of makes sense. But quite crucially still, there are these parts of the embeddings where we don't know what's happening, and we also don't really know what the distribution of the classes of the embedding looks like. Now, conversely, if you look at the middle panel, you see what would happen if you actually don't reconstruct. So you don't try to also reconstruct the latent factors, the generative factors into the original data, but only optimize for KL divergence. And what you can see here is maybe not very surprising again, because given a lot of parameters, it's quite easy to just map anything into Gaussian distributions if these Gaussian distributions don't really need to mean anything. So the meaning comes from the fact that you're reconstructing, that you're trying to sort of associate these latent variables to the inputs again. So if you only optimize for just the KL divergence, all you're going to do is you're going to map some inputs to some Gaussian distributions. But as you can see here, there's no sort of meaningful correlation. The interesting thing then comes in the variational autoencoder when you combine these two concepts. So like I said before, if you look at derivations of a variational autoencoder on the internet or in the literature, sometimes you'll start from this perspective rather than from the math from where we've started. I personally prefer the math view a little bit because it, from the start, makes sense in terms of we're learning about the data distribution, we're learning this lower bound to the data distribution, but here you can just see intuitively why we want that. First of all, you can see that maybe you cannot see because the numbers are too small, but what you should have seen if they were more legible is that on the very left-hand picture on the reconstruction loss only one, the x and the y-axis are labeled with something like -30 to +5 and -40 to +35. So the scaling is rather arbitrary because we don't know what the distribution spans. On the right-hand side, in the combination one, we know that we have this KL divergence part. We know that we want our output of the encoder, this approximate posterior that we've introduced. We know we want to press this into a prior, which is a Gaussian distribution. So the x and the y-axis here actually go from -3 to +3, which is the extent that you would expect a unit variance Gaussian, so like 3 sigma, which you would expect it to occupy. And so first of all, this embedding, it fills this Gaussian prior quite nicely, which is really cool because we now have a handle of what the distribution here looks like. And second of all, then you can see that you're crucially avoiding a lot of these holes. Of course, keep in mind, it's still optimization, so it's never going to be perfect. There's some theoretical reasons why this is never going to be perfect anyway, but I would prefer to just skip them here, but just so you are aware that I'm not presenting you a perfect solution here. But on average, we have some grip of the distribution here, And we can then, because it's more dense, we can then have these interpolations where we really go from 1 to 2 to and so on. And it's illustrated on this slide, where rather than seeing this latent space in terms of points on as on the previous one, what you see is you see a grid of a Gaussian, so a discretized Gaussian from -3 to +3 in both dimensions. And each of the z's that you get at this point, what happens when you feed them through the decoder. So what happens when you take a random sample from or in this case, a structured sample from the Gaussian prior and feed it through the decoder in order to generate a real data point. And so what you can see is, first of all, that there is a real data point that gets generated. And you can also see that because of the structure of this latent space, there are these nice interpolation properties. So from the top right, you start going from maybe a slightly tilted one to a less tilted one to a 7 on the left. If you go to the bottom, you'll go to like a more tilted one, which somehow rotates into an 8, which then loses some of the parts on the left to go into a 3, which then loses some part to go into a 5, and so on. So it's quite nice that you have, first of all, these interpolation capabilities that you would like embeddings to have. And second of all, you can actually sample from this prior distribution because you've pressed your encoder into producing this prior distribution. You can sample from the prior distribution without calculating the encoder in order to generate a data point that should resemble something that you'd observed during training. And this is the reason why we've taken this sort of very long detour to introduce generative models, but also introduce variational autoencoders a little bit more formally, because what we can now take a look at is how does this fit into continual learning? And specifically, there has been a very seminal work called variational continual learning, variational because it's from this variational inference perspective. You don't actually necessarily need to use a variational autoencoder for it. You could use other variational neural models. I just like the autoencoder because it's still decently easy to introduce and talk about. But let's just take a look at why this is now so cool for continual learning. So on the top, you just see this this elbow, this evidence lower bound, this lower bound to the data distribution as the loss of the variational autoencoder again. And we can now think about how having these two terms, on the one hand, this reconstruction loss, this likelihood of a data point being generated by a generative factor, and on the right hand, this callback labler divergence, this way to measure how close our approximation is with respect to the prior that we've chosen, we can think about how this is really, really nice to have for continual learning. And so the first perspective is what is referred to in the literature as the likelihood focused perspective. It's the likelihood focused perspective because we're going to take a look at the term that evaluates the likelihood of X given Z. So a data point coming from a generative factor. And this part is nice for continual learning because what we can do is, what we've just said is we can take a sample from the prior, we can generate a data point of an old task, and we could now, similar to the subset rehearsal that we've talked about in the beginning, this exemplar rehearsal, we could just concatenate this data point to the new task and then keep on optimizing. So it would make sure that this likelihood sort of remains the same. It remains the same during the original training, whereas if you continue training, it would also remain the same on these generated, on these rehearsed examples. So it's a very, let's say, natural way to introduce this generative, this pseudo rehearsal idea into our framework. But interestingly, and I think that's the more sort of nice take of why I also chose to introduce a variational encoder, autoencoder, rather than, for example, a generative adversarial network, is that we also have this KL divergence term. And this KL divergence term, again, what it's telling us is that we're going to optimize the distribution, this approximate distribution that is produced from the probabilistic encoder to take on the form of this prior that we've chosen. In our case, in this example that we've just had, a Gaussian distribution. And so what we could now say is that we have a handle on the type of distribution that the embedding will occupy. So if we think of continual learning and these ideas of regularization and knowledge distillation from the previous lecture, we could also ask ourselves, if we know the form of the distribution that an old task has now occupied, we could also use this to regularize it, to let it change less or not change, to remain like largely stable and less plastic over time when we start learning on the new task. And a very perhaps intuitive way to do that in variational continual learning is to start learning on the first task where we just pick a prior, such as the unit Gaussian that we've chosen, and start the optimization to have the approximate posterior take on this form. And then in the consecutive step on the second task, we'll no longer use our initial prior, we'll actually use our approximate posterior of the first step that we ended up with. So we'll just have we'll replace this KL divergence term with the approximate posterior from the former task that we had, and then plug it in and make sure that we just don't deviate from this too much, because it's the embedding that we would like to preserve. So we can see that this, or we can take a look at, okay, before I take a look at this, wrong direction, I've had a question, which is on YouTube, which is, wouldn't the noise type in GANs also enforce the same effect? I think GANs are a little bit of a complicated story, because GANs will also somehow learn about the distribution, but they'll not do so very explicitly like shown on the last slides, but they'll do so more implicitly through this idea of, so just as a recap, a GAN also consists of a decoder, a generator, and an encoder, but usually you don't optimize GANs to explicitly approximate the distribution, but generative adversarial networks are optimized by having a classifier on top that checks whether the input is real or has been generated by this decoder, so whether it's fake. It's still going to implicitly learn about the distribution. And in fact, if we don't look at papers from 2018 in continual learning, if we just were to take a look at papers in 2019 or 20, we'd see that the majority of approaches of VAEs and GANs is anyway sort of intermingling into one single model where you kind of get the best of both worlds. Yes, you could also use like a variational GAN. You could also use the GAN itself. Now, keep in mind that if you are familiar with GANs, in the traditional formulation of a GAN, you would have potentially a mode collapse problem. So in contrast to a VAE that really very explicitly has this notion of reconstruction and this KL divergence that needs to like envelope everything that you've seen, a GAN does have the choice to just say, oh, there are like these 5 different modes of the data, but this one is very easy to optimize, so I'm just going to concentrate primarily on this mode, and all my images are going to look like this, or all my sound types are going to appear like something else. So there's this idea of mode collapse that could happen in GAN, which is why I, at least for the tutorial purpose here, prefer to talk about variational continual learning. But as I've said, keep in mind that there are variational autoencoder adversarial networks. There are ways to just include adversarial losses in autoencoders in general. There are also ways of how to measure distributions more explicitly in GANs, and there are Wasserstein distances and so on. So it gets, let's say, at some point these models become quite similar again. So yeah, you'll find maybe equally many variational continual learning approaches as well as GAN-based continual learning approaches in the pseudo rehearsal literature. Let's take a look at how this works. So first of all, in variational continual learning, and that is another reason why we've presented it here, we've just seen that this KL divergence term on the right-hand side, this prior focus perspective, it allows us to very intuitively have this regularization perspective. And so for that reason, it's quite natural to maybe also compare it to these elastic weight consolidation and synaptic intelligence ideas that we've talked about in the last lecture. So recall that there we've said that in synaptic intelligence, we take a look at trajectories of how parameters change, and then the ones that have changed a lot, that have contributed a lot to the loss, are very important to constrain. And similarly, in elastic weight consolidation, we'd calculate something like the Fisher matrix, some importance matrix of the parameters to again have a constraint on the parameters. And now quite similarly in variational continual learning, we could have this idea of having such a form of constraint on the prior task, on what's important for the prior task, through this probabilistic encoder by constraining the latent space, the posterior we have obtained on the previous task. So in that sense, it fits naturally into this regularization perspective as well. And so in this arguably maybe relatively simple task of permuting these MNIST digits over time, the variational continual learning work has respectively, maybe because it's a little bit more explicit with this entire regularizing the approximate posterior parts, is a little better off than the synaptic intelligence or elastic weight consolidation perspective if you just look at VCL in the blue curve. Now there's also, and that's the interesting part, there's also a VCL plus random core set and the VCL plus K-center core set idea here, that we're going to talk about in a second. So what this means here is that in addition to having the means to regularize naturally and the means to maybe also generate data naturally, we could still, of course, think about this perspective where we've started in the beginning of this lecture of retaining original data elements. And in fact, VCL has put this on top as a like third component. It's called core set. We'll talk about in a second why it's called core set. But just here, again, maybe not surprisingly, that if you add another memory buffer of real data in the purple curve to the blue one, it's going to go to the top to the extent that you're actually almost solving the task. And also what you can see is the random core set only part, which is if you just have the memory buffer, you can see that it's doing somehow well, but putting these regularization perspectives and generative perspectives on top still helps you. You can also see what we've observed earlier in the ICARL diagram, that of course there's no change in this conclusion here, that the larger the memory buffer we have, the better the performance we're going to achieve. So of course, even in a variational autoencoder and all this variational inference perspective, the value of data is still pretty much there. So if we're choosing to store real subsets of data in addition, more data is still better. But maybe let's talk about this now that we visited all this math. Let's talk about this more data in a slightly more formal way of how to store auxiliary memory buffers and subsets of data. So you've already seen on this previous two slides that in variational continual learning, they set core set. So it's not like an ICARL where they say prototypes or exemplars, they actually call it a core set. And first of all, before we get to the actual definition of what a core set is, keep in mind that a core set, especially in the continual learning literature, will be used extremely loosely and often very synonymously with exemplars or just subsets of data. But formally, if we look at the real definition of what a core set is, it's actually, let's say, the scientific question, the mathematical question underlying this entire idea of rehearsal, of picking out subsets of the data, because a core set is defined as a small, sometimes weighted summary of large data sets, such that the solution found on the summary itself, so on this subset, is provably competitive, so emphasis on provably competitive, with solutions found on the full data set. So if we think of back of the GDUM paper, this greedy dumb learner that we've briefly seen at the beginning of the lecture, where they've done this experiment of let's have a greedy way to populate our memory and then train a new network on it, and we find out that this is actually just as good as if we had just learned continually. then this is going a little bit in this perspective that what we're actually trying to find, if we think of the scientific question, is the most meaningful subset of the data, that if we train on the subset, we get the exact same solution that if we were to train on the large data set, on the entirety of the data set. Coming back to, of course, the way that the data is distributed, some data elements are worth more than others, and so on. And crucially, and this is what we'll always have to keep in mind, is there's no universal way to populate a memory. There's no universal core set in that sense. It's always specific to some data. It's always specific to some set of questions, some set of tasks that we assume. It's always specific to the type of model that we choose. And it's specific to the loss or cost functions that we have, because we're asking ourselves, is it provably competitive to find a solution for a specific task on a subset of a full data set? So it depends on all of these factors. And so in that sense, maybe the herding algorithm of ICARL, maybe to give it a little bit of benefit of doubt, has been shown that it's not better than random sampling in the particular instance that ICARL has considered in this diagram at the start. But that doesn't necessarily mean that the herding procedure itself is bad. Maybe it just means that the herding procedure and this idea of populating the memory buffer according to means one by one, maybe it just hasn't been particularly useful in this combination of model choice, task choice, loss function choice, etc. Just to give it a little bit of, to lift it up again. If we take a look at this, let's say intuitively, I've prepared, or I've taken out two visual examples from my own survey paper. I'm mainly just picking them out here, to be honest, to give you a nice visual illustration, not really because there's some sort of elaborate scheme behind it. But let's just think about this from a 2D perspective. So we can ask ourselves now that we know the notion of core sets and we've just seen variational continual learning, then the idea in variational continual learning is that we have a grip on what the distribution in our latent space looks like, right? So we've said we would like to have this posterior be pressed into a Gaussian distribution. So taking back a look at these 2D latent spaces, one is illustrated here, we can see that this particular one has 4 clusters. And the distribution of these clusters on both dimensions is illustrated on these side axes in the respective colors in the solid lines. So you can see that there's a particular shape that they occupy. They're more or less Gaussian-like, I would say. And what you can also see here in these X's, in these black crosses marked on this diagram, is what would happen if you let this herding algorithm run to pick, I think it's like 100 or 50, I think it's 100 exemplars here. So fill a memory buffer one by one with 100 data points based on this herding idea to always best approximate the mean. And you can see that, well, maybe it's doing an okay job at having some specific properties, but what it's actually not doing is it's not reflecting the distribution. So the discrepancy between the dashed black lines, which corresponds to the distribution of the actual picked exemplars, and the real distribution in this latent space is quite large. And that is, of course, because these algorithms, like you could take a random k-means, for example, and just use the k of the k-means as each as an anchor point and select the data element that's closest to this k. There doesn't need to be a data element that's very close to this k, so you could make a mistake. And B, it doesn't necessarily, maybe, at least in this herding point of view, it doesn't necessarily account for the distribution. It just cares about whether you approximate the mean well. It doesn't care about whether you capture all the tails and the shape of the distribution and so on. So alternatively, the question would be now, in variational continual learning, or in variational autoencoder specifically, if you know specific properties of how your latent space is distributed, if you know how the mathematical formulation of this looks like, maybe we could also take samples from this posterior. So rather than doing this algorithm of herding and estimating the mean, maybe we could do something like we could take samples of this posterior, we get some z values, and then pick the original data elements that lie closest to this. And so if we do that, and this is again just an illustration, I'm not going to sell this to you as the absolute solution. There are some issues with this, and it's maybe not as intuitive in super high dimensions as it is in this 2D example. But I just want to illustrate to you that having this notion of a distribution rather explicitly, and this variational continual learning, or rather in general, in generative models that just approximate the distribution in the first place, is beneficial or can be very beneficial even for discriminative tasks, not only because we have this idea of generative replay, so pseudo rehearsal, not only because we can integrate this regularization perspective a little bit better, but also because knowing about the distribution would then in turn let you select data subsets more carefully, in the sense of that the data subsets actually approximate the distribution better. So here's another example where we do actually the sampling process and just illustrate that if we then pick the closest data points, the dashed black lines of the distribution of these picked original data points are in fact a rather good subset in terms of approximating the overall distribution. Now, keep in mind, this still doesn't guarantee to you that this is a core set, because it still doesn't guarantee that if you train on this particular subset now, you'll get the exact same performance in the end, which is a criterion, or at least with an epsilon of this performance. But at least what you could do now is you could argue that the way you could pick and populate these memory buffers comes closer to what the actual distribution looks like, which at least to me is a lot more intuitive than picking some, let's say, less motivated heuristics. So to wrap up the variational continual learning part, there's also a third, or let's say fourth even, thing that you could do, and this comes down to the let's say modifying the architectures and dynamic models that we'll get to in the future lectures. You could also think about, rather than having these regularizations in terms of the posterior, you could also think of just allocating a different prior for a different task. So think of, if you have this like two-dimensional latent space, you could say that you pick a prior for task 1 so that it falls here, you pick a prior for task 2 so that it falls here, and so you could actually make it such that it's not necessarily completely overlapping in the first place, and you could control this a little bit more explicitly, given that you know the prior distributions for different tasks and the posterior distributions. You could also avoid forgetting to a larger degree then. And so continual unsupervised representation learning, or short CARL, has actually shown that this can be a very nice scheme, where they have in fact chosen to have task-specific priors. So for each and every single task, they just introduce a different prior and optimize the KL divergence such that the encoder maps into it for this specific data, assuming, of course, that you have enough parameters so that your probabilistic encoder is so large that it can map to like all these different complicated distributions that you have that you wanted to have in the first place. But again, if you do make the choice that the probabilistic encoder is some very complex deep neural network, this seems to be a very reasonable assumption. So to wrap up this lecture, the couple of last minutes, and I understand this lecture today is going to be a little bit longer than the former ones. I hope this is okay with everyone who's listening, is I've kind of sold you pseudo rehearsal first with a little bit of a skeptical view, but then we've taken it back again to almost like overselling it in the sense of believing that maybe we've now solved continual learning. So because variational continual learning now sounded like, wow, we can do regularization and distillation in a natural way. We get some knowledge of the distribution, so we can pick exemplars maybe more holistically. We can do pseudo rehearsal and generate examples, so we could even have that. And it sounds a little bit like it's a win-win-win-win. So the question would now be, maybe it still is a win. So I'm quite convinced that this is a good approach. But the question is still, why are we not done? Why is continual learning not solved? Or at least, why is continual learning not solved if we think of the catastrophic forgetting challenge? Keep in mind, we'll talk about the other challenges in the next lecture as well, like these overconfidence phenomena that come into play in addition. But looking at catastrophic forgetting, we can still ask ourselves, why is this insufficient, or why has this not taken off as much as we would maybe expect it to from the theory and from the math point of view. And there are a couple of different perspectives on this that I would just like to wrap the lecture up with today. And the first one is that if we take a look at generations, we now have to keep in mind that if we want to have pseudo rehearsal, so generate data in order to avoid forgetting, so we generate data and we keep training on it, and in the next step we learn how to generate on this data and some new data and keep training on it. It's can very rapidly get into like a snowball style effect, where if you look at the specific example of CIFAR images from a nice paper that has investigated the role of generative models from a perspective for continual learning, you can see that maybe in the initial task one, I understand the images are quite small, but you can see that there are airplanes being generated on these 32 by 32 thumbnail pixelated images. And then the second one will add cars to it. But the problem, of course, is that during the second task, unless we again want to store all the data, but then we would have just stored our original data maybe, we would now in task two need to relearn how to generate from whatever we've already generated in task one. So in that sense, if we make small errors, they'll start accumulating maybe more rapidly and more rapidly. And already at the task three, but at latest at the task four on this illustration, we can see that whatever our neural network here now generates no longer really resembles anything that is useful, or at least no longer resembles anything that is intuitively and practically appealing. So generative replay has its limits in the sense of how powerful are our generators, how many errors snowball, how fast do errors accumulate. Similarly, or let's say on the reverse perspective, we see that on the right, again, it's the same, or it's a similar image. Generative replay will have this forgetting issue because generators also forget. But we also maybe have a similar issue in terms of rehearsal if we think of memory buffers. So if we have a memory buffer that's quite small and we store original data into it, and we look at, for example, what networks generate as a proxy to sort of the distribution they've learned, and we then start drawing random samples from it, we can see that there are a lot of same images in this case here. And that's because, of course, if you only keep on showing a very small subset of images or of data in general to this generator, to these solvers, then there's a good chance that at some point they're going to forget about all the other tails of the distribution if the exemplars don't really cover this entire distribution very well, right? Like what we've seen in these 2D examples. In that sense, you start just overfitting to these exemplars, and you will again start losing information, start having some sort of gradual forgetting, at least, if not even catastrophic forgetting, because of this. And of course, naturally, fine-tuning, we already know, is just going to override everything. So if you fine-tune on a generative model, even on the second step, it doesn't even know what a car is anymore. It's just going to, what an airplane is anymore. It's going to start producing cars. So I said in the beginning that we've tried to look at examples first and then discuss desiderata and like our wishes later. And so now on the sort of remaining stretch of the lecture, I would just like to briefly think about what could be our expectations and what could be the things that we actually desire, especially now that we've seen so much information and at least two particular examples of exemplar rehearsal and generative rehearsal. So in the interest of time, because I'm already quite into the lecture, maybe I'm just going to list them. But if while I'm listing them and going through them, there's something that you have in mind, feel free to, of course, mention this in the live chat and we can discuss this in addition. But just to give you a bunch of really questions, because in my opinion, I want to be quite open about this. It's not clear to me, I don't think it's clear to the majority of experts right now, which of these items weigh more than the others, and which of these items are particularly necessary given specific scenarios and which ones are not. So I'm fairly sure that there's no consensus on like this general grand scheme of things that we want, and maybe more sure that given a specific applications, there are some things that we maybe can accommodate and some things that we cannot. So, for example, constant memory budget is a good example where we could say, first of all, do we want a memory budget, or do we worry about privacy and so on? But second of all, if we have memory allowed, then do we need a constant budget? Or maybe as tasks go, we can also grow our memory budget. If you think of a constant memory budget, then of course there's a natural decay in what I've shown on the former slide in terms of rehearsal, because if you start with 100 data instances on the first task, already by the time you're reaching the fourth task, you're only going to have 25 samples left of the initial task if you assume that you're balancing this. So there's a natural way of forgetting again and overfitting to these quite particular exemplars over time if you have a constant memory budget again, and this isn't extremely large. But then again, it's a question of maybe if you're in robotics and you're doing embedded computing, maybe you do have a constant memory budget. Maybe if you're thinking of extremely large-scale transformer, whatever models, large-scale language models, maybe you don't so much. Then similarly, you could go through all of these items, like pragmatically, what you want is maybe just a selection algorithm for this to fill this memory budget with items that then do better than if you were to just randomly populate these items. You'd maybe pragmatically want some way to shrink this memory buffer as soon as you add new tasks. Maybe more formally, or more ideally, you would like to have some notion of the knowledge of distributions and some subsets that you select that actually have approximation guarantees, like we've discussed in the core set idea. And respectively, maybe then you would recursively apply your selection algorithms rather than doing this chop off as an ICARL, where you just say, I'm going to chop off half of my list. Maybe you'll just have a core set and then you'll apply the core set algorithm on it again to find again now the subset that best approximates the already selected subsets. And then, of course, we have to keep in mind that there are many formulations, right? So maybe we don't only want to think about, is it regularization, is it distillation, is it pseudo rehearsal, is it exemplar rehearsal? Maybe we also want to find some natural formulation that allows for various of these ideas at once. So that was the reason why I wanted to present to you variational continual learning, because I personally believe it's, let's just say it's an interesting idea to try to think of how these perspectives can be combined, can be naturally interpreted from a single perspective. And so with that, I'm just going to present, let's say not present, but just pop up two final examples to end the lecture on this last thought of combining ideas. So keep in mind, we've now covered in two lectures, we've covered regularization and knowledge distillation. We've now covered exemplar rehearsal and pseudo rehearsal, like generative replay. We've covered a little bit of how these ideas maybe fit in together. And if you take a look at the majority of, let's say, empirically oriented papers nowadays, you'll find a very large amount of works that do in fact combine various ideas. So this is an idea of lifelong GANs, so conditional continual learning for continual learning for conditional image generation, where you can see, without going into all the details of what this precisely means and how it's implemented, already between two time steps, they do actually have a variational autoencoder here. They do also have a GAN, which I'm not showing on the slide because it's just too much, but it works in a similar way. But for this, they really put in almost all that we've talked about so far. So they put in a knowledge distillation loss, not only on the input-output relationships, but also with respect to this Z that they get. So this approximate posterior, like we've discussed in BCL, where you make sure that the posterior doesn't change too much. They also put in addition, they get data from new tasks, but also have auxiliary data. So they also store like memory buffers. They also generate data to put it in as well. So it's really just putting in all of this at once, kind of assuming that each and every individual of these elements is going to capture some aspect that the other one has not yet captured. And then of course, if you combine all this together, it starts working quite well empirically, assuming that whatever machine learning model you've started with has enough capacity, has enough parameters to just keep on learning without forgetting. And the second example that I wanted to show, just also to get a little bit away from just talking about images, is you can almost seamlessly transfer these concepts to other ideas like reinforcement learning. So we've seen supervised learning, we've seen unsupervised learning. You'll have the same in reinforcement learning, where here it's about deep Q learning, where you can see that in addition to this like DQN agent, they'll have this like staged training cycle where first they train the DQN cycle with some experience replay. So it's again like real experiences, but they also train a generative adversarial network that then loops back generated data. So even in like deep reinforcement learning, you'll have these same ideas, you'll have these same combinations. So what I really want to have as a disclaimer and maybe as a note is that a really big portion, at least from what I've seen, of present continual learning works do in fact use rehearsal. They use it in all various ways. They combine various ideas in multiple ways, and they come in all shapes of like supervised, unsupervised, reinforced learning, in addition to all sorts of modalities of is it images, is it audio, is it language. But these ideas of these pseudo rehearsal, exemplar rehearsal, distillation, regularization, they do seem to be quite common throughout literature nowadays and go like hand in hand with each other in various works. So in that sense, at some point, maybe the continual community is going to start asking how to continue combining these methods in a natural way, how to consolidate this all into a single framework. But really for now, at least if you were to ask me as like the final question of this lecture, after talking for 4 hours sort of about catastrophic forgetting, what the best method would be, the only thing I would possibly tell you is that there are so many ways to alleviate catastrophic forgetting. It depends extremely highly on the specific task, the models, the data that you have. All of these cover maybe different nuances, different niches. If it's just about pragmatism, potentially combining ideas is a good way to go. If it's about the theory, then there exist some approaches like variational Bayesian inference that maybe allow for more natural formulation than others. But it's always as well a trade-off between how formal, how like theoretically nice can you get, how empirically good results do you get. So it's a question of emphasis here. And with that, I want to end the lecture today, and I want to end in that sense the section where we talk about catastrophic forgetting. Maybe you'll be a little bit surprised about the fact that we are not talking about these extending models and adaptive dynamic model architectures immediately, although it's advocated as like one of the 3 branches of how to avoid catastrophic forgetting. As I've previously mentioned, although it is advocated as one way to avoid catastrophic forgetting by like freezing parameters, putting additional parameters on the side, connecting them, I believe it's a more sort of general principle to think about dynamic models. So we're going to talk about active learning next first, before we later circle back to dynamic models because they'll just play a more general role. So next time, like I said, we'll talk about active learning. In my opinion, it's a little bit like of the flip side of catastrophic forgetting, where we've talked a lot now about how does knowledge transfer, how do we maintain knowledge, but now somehow the question that we've never asked ourselves so far is, where does the data for our next task actually come from? So far, whatever we've seen, like even these incremental digits, we've always just assumed that someone gives us a data set and then in the next task tells us this is your next data set, and then the next task tells us this is your data set. So from next week on, we'll spend some time on figuring out how can we automate or semi-automate this selection process in terms of picking future tasks, picking future data. And with that, I'd like to thank you for your attention and see you all next time. If you have any questions, feel free to ask in the YouTube chat now, or feel free to ask in the Teams chat. Yes, so there is a question about the exam for this course, but maybe this one you can email me and we can take it offline because it's maybe not the best idea to discuss this live on YouTube. I would appreciate that, but thanks for the for the hint about like the second exam date that we'll have. I'm sure there will be one, so I just need to figure out. But just send me an email just to be on the safe side, so I don't forget to ask about this. Or obviously, feel free to, if you're a student who's taking the exam, feel free to tell me in person also. Okay. So I think if there are no other questions than this one, I'm going to end the YouTube live stream now. Of course, after the YouTube live stream is ended, feel free to ask on Teams.